So green chemistry is clean chemistry, or we can say pollution-free chemistry, sustainable chemistry, and hazard-free chemistry. So at present, we enjoy several products which are being prepared with one or another organic chemical reaction, or we can say organic synthesis. So we have listed several products which we use in our daily life, right from say plastics, then rubber, then major domain is pharmaceuticals, means medicines we take. All these are organic compounds, right? Then perfumes, uh, dyes, okay, pesticides, insecticides, several food products, food additives. These all are organic compounds, and they are being prepared from petrochemicals. Okay, so their origin is petrochemicals or petroleum oil, and that petroleum oil is what? It is depleted. Okay, one day it will be over. There will be no more petroleum oil, so no more petrochemicals. So we cannot manufacture these products which we are enjoying in our daily life. Okay, so that we don't want. So that is one reason why green chemistry. So we want sustainable chemistry. Okay, so presently we use petroleum-based chemistry, which is not sustainable, which will be exhausted, depleted. Okay, this is one aspect or one significance. And another is present organic synthetic routes, which we use in industry for manufacturing of these products. So those are hazardous, okay, and they create pollution to the people living around the industry, we consumer, and also to nature. Okay, so we don't want this. So presently, we experience several environmental issues, right? So these are all outcome of this vast use of petroleum products. Either in a vehicle, we use petrol, diesel, they create global warming, right? Greenhouse gases and global warming consequently. That is one aspect. And another is when we use these organic compounds, they are hazardous in this or that way. Okay, so we don't want that hazard to the person working in the industry, person staying nearby the industry, we consumer, and also to the nature. Okay, so green chemistry suggests 12 principles. So we need to design our synthesis. Okay, we have to change the conventional route. Previous route we have to change because they are hazardous. So green chemistry suggests 12 principles for the design of chemical synthesis in such a way that there will be no use or less use of petroleum product. That is one thing. Another thing is that should be sustainable, okay, and not harmful to anybody, not to the human, not to the animals, not to nature, trees and all, right? So accordingly, 12 principles I already discussed in short, in brief, right? So these are the 12 principles. Okay, so we were discussing these first two principles. First is waste prevention and atom economy. So we were at atom economy, and atom economy is largely related with waste only, or waste prevention principle only. Okay. 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 So last time we defined atom economy principle. This principle number two. Okay. So what atom economy says? So to understand atom economy, you should know the structure of reaction that I already told you. What is structure of a reaction? Let me write again for revision purpose. See, structure of any organic synthesis which is based on petroleum product or petrochemical. So we have reactant, right? Then we add some chemicals to reactant. Usually we call them as a reagent, right? Then there are reaction conditions specified above arrow. Okay. That may be temperature, maybe pressure, maybe catalyst or solvent, etc. So these are again conditions to perform the chemical reaction. So what we get is product, right, and also byproduct, right. So all 12 principles of green principle chemistry, they are moving around this skeleton of organic synthetic reaction. Okay. So if you know this skeleton, okay, you can write significance of any principle of green chemistry, right? So in this skeleton for the organic chemical reaction, here the reactant is petrochemical, reagent sometimes a petrochemical, this solvent is petrochemical. Okay, so we use petrochemicals as a starting compound, right? That is one case. Another case is we end up with byproduct along with product. So this byproduct is actually waste, and this is correlated with the first principle of green chemistry, waste prevention, right? Okay, this waste prevention. So organic chemical reactions, they always involve byproduct. Okay, so byproduct means it's a waste. This is our desirable product, major product. So our atom economy principle is based on this skeleton only. So let us define it. So what atom economy says, all the atoms, all the atoms present in reactant as well as reagent should be transformed into major product and not in the byproduct. Okay. So that is what the basis of atom economy principle. But unfortunately, we have byproducts which are always produced in several or many organic chemical reactions. They are unavoidable in many organic chemical reactions. So we are wasting atoms which are present in reactant or reagent. So that is what atom economy principle says. So uh, atom economy should be as high as possible. Actually, it should be 100%. Means we should not waste atoms present in reactant as well as in reagent. All should be converted into desirable product, means major product and not the byproduct. But it is not happening always. Okay, we get byproduct. So that is the basis of atom economic principle. So accordingly, last time we studied this principle with respect to synthesis of one of the industrial important product. So let us go to that. So we understood the formula for the calculation of atom economy or percentage atom economy. So we usually define it as a molecular weight of product, molecular weight, molecular weight of product divided by total molecular weight of all reactant. See, reactant, not catalyst, not solvent. You see, you should identify which are the reactants. Okay, and those you should consider, or their molecular weight should be considered. So, molecular weight of product at the numerator divided by total molecular weight of reactant into 100. Okay, so here important thing is what molecular weight calculation. So, to calculate molecular weight, you must know correct molecular formula. Okay. So we studied atom economy principle, or we are studying actually, we are not finished at all. So we were studying preparation of maleic anhydride, one reaction intermediates. Okay, it is utilized in the manufacturing of several drugs, this medicine, and also insecticides. So this is an industrial important product. So actually, it is intermediate. This is not a final product. This is intermediate. We perform reaction on maleic anhydride and we get final product. Okay, but This is what the, I mean, very simple example to understand atom economy principle. That is why we took this example. Okay. So maleic anhydride can be prepared by the following methods. Okay. Let me take arrow. So maleic anhydride can be prepared by the following methods. First is oxidation of benzene, second oxidation of butene, and third is oxidation of butane. So reaction type is same, oxidation only. Okay, in all three reactions, it is oxidation. But reactants are different. In the first case, we have benzene. We oxidize benzene and we get maleic anhydride, and then we will calculate atom economy using this formula. Then we will take butene. We will oxidize it. Let us see what is the effect on atom economy, whether it increase or decrease. Okay. Then in the third case, we will take butane. Okay, we will oxidize it and we will see what is the atom economy to produce maleic anhydride from it. Okay. So first, this we already did last time, oxidation of benzene. So let us have a quick review. Uh, Benzene is C6H6, and this is a structure, okay, ring structure. So we have to oxidize it. Okay. So I wrote O2. I don't know how many molecules are required. That we will balance out okay, later on. Then for oxidation, I need catalyst V2O5. So V2O5 is actually catalyst. It will not take part in reaction. Okay. So we will not consider its molecular weight. Okay. So here we have total molecular weight of reactant okay, at denominator. So we will not take V2O5 molecular weight. This is what important thing you should know. So this is not reactant. Okay. We want reactant in our formula and not catalyst, because catalyst never takes part in actual reaction. Okay. So benzene plus will be oxidized in presence of V2O5 and we will get maleic anhydride. So as I told you last time, just by looking at the name of maleic anhydride, we cannot write its structure. So you must know the structure of maleic anhydride. I would say correct structure of maleic anhydride. You should not miss single atom or single bond. Okay, all everything should be intact because we are talking about atom economy. So we should not miss any atom and also any bond. Okay, so this is what the structure of malic anhydride, and along with that we guessed there are byproducts. Which are possible byproducts? So that can be guessed by looking at the structure of benzene and the structure of malic anhydride. So if we look at the structure of benzene, we could see 6 carbon atoms in the ring. Okay. So in reactant there are 6 carbon atoms, but in product we have only 4. 1, 2, 3, 4. So 2 are missing. So definitely there is a byproduct, and probable byproduct is carbon dioxide. So we wrote for carbon dioxide. Okay. 2 are missing. So 2 carbon means 2 CO2. That you can easily write. Okay. Now, what about hydrogen? Because benzene contains hydrogen also. 6 hydrogens are there. Okay, you could see here. So, in main product, malic anhydride, we could see only 2 atoms, 2 hydrogen atoms. One over here and another over here. So, 2 hydrogen atoms are only converted into desired product. Here there is no hydrogen. Here also no hydrogen, and at this place also no hydrogen atom. Only we have 1, 2, 3 bonds means fourth one is a hydrogen. Here also 1, 2, 3 sigma bond means fourth is a hydrogen. So 2 hydrogens definitely we have in this desired product. So only 2 are accommodated. So it means 6 minus 2 means 4 are missing. 4 are wasted, and probable product. When we talk about oxidation, probable product with hydrogen is water, H2. You can easily guess it. And we have 4 hydrogen atoms. So 4 hydrogen atom is 2 water molecules. Okay, so that logic you can easily apply. You understand? So you don't have to mug up this reaction. Only thing is you should know this malic anhydride formula. That only you have to keep in your memory. If once you know that, okay, the byproducts Yeah, you can easily write by just counting carbon and hydrogen in the reactant benzene. Okay. Now we will balance out oxygen number that we have that we did not balance. Okay, only one oxygen molecule is not sufficient. So that number we have to balance. So finally there is balancing of oxygen number. Okay, not initially. You don't have to mug up this reaction. Okay. So now you count oxygen atom at the product side. Okay, product and byproducts. All oxygen we should count, and those oxygen atoms should be supplied at reactor site. Okay, so let us count oxygen. One, two, three in major product. Three oxygen. Here 2 into 2, 4. 4 plus 3, 7. Plus 2 means 9. I want 9 oxygen atom at the product side. So I must supply 9 oxygen atoms at reactant side. So 9 oxygen atoms I want means 9 by 2 molecules because one molecule is O2. Okay. So 9 by 2 means 4.5. Okay. Now भागिले 2 मध्ये किती 4.5 होता. That is what I must supply 4.5 molecules of oxygen. Listen carefully. 4.5 molecules of oxygen per molecule of benzene. एका बेंझिन मॉलिक्यूलला 4.5 ऑक्सिजन मॉलिक्यूल सप्लाय करायला पाहिजे in presence of V2O5 catalyst, then you will get one molecule of maleic anhydride. So definitely you can guess its atom economy is not that good. We are wasting several carbon, hydrogen and oxygen atoms. Okay, so whatever it may be, we should calculate exact atom economy. So if you look at the formula for atom economy, we could see there is a molecular weight of product and total molecular weight of reactant. So we are talking about molecular weight, so we should carefully write molecular formula. Okay, so benzene is very easy, C6H6. Okay, then oxygen is straightforward, 4.5 O2, so no problem there. Now in this case, in case of maleic anhydride, you could see one carbon over here, 1, 2, 3, 4. So C4. Okay. So what about hydrogen? Here there is no hydrogen, no hydrogen, no hydrogen. Here we have one hydrogen because three bonds means fourth one is a hydrogen. Here also three bonds means fourth is hydrogen. Means H2. Okay. C4, H2 and O 1, 2, 3, O3. C4, H2, O3. Okay. So you should correctly identify hidden hydrogen atoms, hidden carbon atoms. Okay, and you should write correct molecular formula. And remaining CO2 H2 are as it is. So once you do this, your almost 90% job is over, right? So now molecular weight of product. Product means what? Only this maleic anhydride, not byproduct. So molecular weight of product we should calculate. You should substitute at the numerator, okay, and divided by total molecular weight of reactant. Reactant, how many are there? Benzene and oxygen, and not V2O5. These two. You must calculate correct molecular weight of these two compounds. Okay. So that we did last time. So benzene C6H6 means one carbon is 12. One carbon atomic weight 12. 12 into 6. Okay, plus one hydrogen means 1 into 6. So you combine it, we get with 72 plus 6 is 78. Okay, you should calculate very carefully. Then oxygen molecule, so one oxygen atom is 16, so 2 means 32. And maleic anhydride C4 means 12 into 4 plus 2 plus 1 oxygen is 16, 16 into 3. Okay, so accordingly we get 98. Okay, then atom economy will be molecular weight of product upon molecular weight of total molecular weight of reactor into 100, so that becomes 98 is a molecular weight of product means molecular weight of maleic anhydride upon total molecular weight of reactant means molecular weight of benzene means 78 plus molecular weight of oxygen, all oxygen atoms. Okay, there are 4.5, so we must multiply this by 4.5, 4.5 into 32. Okay, so 78 is a benzene, okay, plus we have 4.5 oxygen molecule there in a balanced reaction. So 4.5 into one molecule is 32. one oxygen molecule is 30. 16 into 30. So this is what total oxygen weight into 100. So we get 44.14%. So this is not even 50%. So atom economy is very, very poor. 44.14. We are wasting several uh, carbon, hydrogen, oxygen atom. Means we are wasting raw material. That is not affordable to the industry. So this is not preferable route. Okay. So let us move to the second case where product is same. Okay, maleic anhydride product is same. Only reaction is also same, oxidation using V2O5, but reactant is different. Reactant is now butene. Okay, so butene is what? The four carbon compound. But means four carbon compound. In means what? Double bond. Is what? Double bond. So we should write it this way. You see, but means 1, 2, 3, 4 carbon. Okay, and there is in means I should write one double bond. Now remaining are hydrogen. Okay, we should able to calculate hydrogen. So here there is one carbon by, so one carbon attached to one bond. One bond. Okay, one bond means three vacancies are there, three valencies are there, which are not occupied yet. So three hydrogen must be there. So we have CH3 group over here. Here one hydrogen because three sigma, one hydrogen is remaining. Okay, here 1, 2, 3 is one hydrogen is remaining, and here one sigma bond attached to carbon means must be three hydrogen. Okay, so this is butene. Then our reaction skeleton is same. Reactant plus oxygen in presence of V2O5, we get maleic anhydride. This is fixed. Okay. Now let us look at the byproduct or possible byproduct. So for that purpose, you should look at the structure of reactant. So reactant is butene. So carbon atoms 1, 2, 3, 4. Just look at the product. Carbon atoms 1, 2, 3, 4. Means all four carbon atoms are transformed into desired product.
Many,
Maleic anhydride. So
many.
there is no wastage, right? There is no wastage of carbon atom. So no CO2 will be produced. Okay. Now what about hydrogen? So as I already told you, here we have CH3 group. These three hydrogens. Here also CH3 group. These three hydrogen. 3 plus 3, 6 hydrogen. 3 hydrogen, 6 hydrogen. Here we have one hydrogen atom attached. 6 plus 1, 7. And here 8. Total 8 hydrogen attached. Okay. So we have C4H8 is a butene, you know well. Okay. So 8 hydrogens. Let us count hydrogen atoms in maleic anhydride. Means how many hydrogen atoms are transformed into desired product. That is maleic anhydride. So here there is no hydrogen. Here no hydrogen. Here also no hydrogen. Only here we could see one hydrogen because this carbon attached to three sigma bonds. Three sigma bond means fourth one is a hydrogen. Here also three sigma bond, fourth one is a hydrogen. Means two hydrogens are there in this whole molecule. Okay, so out of atoms, out of 8 hydrogen atoms in butene, only 2 atoms are accommodated or transformed into desired product. So it means 8 minus 2 means 6. 6 atoms are wasted. Okay, so 6 atoms will be converted into 3 water molecules. 6 hydrogen atoms, 3 into 2, 6 atoms. Hydrogen. Okay, 6 atoms or only 3 molecules use शकतो. So that's all. So this is what the skeleton of reaction. I guessed what are the byproducts by looking at the number of carbon atoms and hydrogen atoms in butene and as well as in molecule. So I guess only water molecules are produced, no CO2 is produced because all carbons are transformed into desired product. Now last task is what? Balancing of oxygen. Okay, that is last step. So let us look at the hydrogen atoms which are there in the product as well as in byproduct. So here we have 3 oxygen atoms, 1, 2, 3, and 3 means 6. 6 hydrogen atoms I want in at the product side. Okay, so I must supply 6 hydrogen atoms at the reactant side. So 6 hydrogen atoms means 6 by 2. 6 by 2 means 3 molecules. 6 by 2, understand? 6 by 2 molecule means 3 oxygen molecules. Okay. Now reaction is balanced. One butene requires 3 oxygen molecules. So in presence of V2O5, we get malic anhydride and 3 water molecules are released. Okay. So here, just at the or just by looking at the reaction, you could guess the atom economy of this reaction is higher than the first reaction. That is starting with benzene. Here, definitely atom economy is improved. Why? Because there is no carbon dioxide produced, no wastage. Okay. So let us calculate actual atom economy. So I already told you how to calculate number of carbon and hydrogen just looking at the structure. C4H8, 4 carbons, 3 of hydrogen over here, 3 at this position. This it becomes 6 plus 7 and 8. So C4H8 plus 3 oxygen we already calculated or balanced out. In presence of V2O5. So this how to calculate carbon, hydrogen, oxygen I already told you in the last reaction. In similar way, it will not change. C4H2O3, molecular weight of malic anhydride, and 3H2 is straightforward. And I told you actually 2H2 we don't need. Okay, in our formula. So percentage atomic economy is equal to molecular weight of product. Product is malic anhydride. C4H2O3 is 98. We already calculated. Okay, 12 into 4. Okay, plus 2 plus 16 into 3. Okay, that whole becomes 98 divided by molecular total molecular weight of reactant. So reactant is butane. Butane means what? C4H8. C4 means what? 12 into 4. Okay, 48 plus 8. Okay, because one hydrogen is 1. So 8 hydrogen is 8. So 48 plus 8 means 56. Okay, therefore I wrote 56. The first reactant, butene. Okay, plus second reactant is 3 oxygen molecules. Okay, so 3 into 1 oxygen molecule. So 1 molecule means how much? 16 into 2. 1 atom is 16. Molecule is 16 into 32. So 3 into 32. That is why I wrote 3 into 32. So this is what? Total molecular weight of reactant into 100. So that becomes 64.47. So if you look at the atom economy is increased from 44%. It is increased up to almost 65%. Okay. So this is appreciable or significant amount of growth in atom economy. So this is affordable to the industry. Industry will definitely take this, this route for manufacturing to avoid waste as well as to enhance economy. Okay. Now third step. Third step is what? Oxidation of butene. Sorry, butene we heard, no? Butane. Sorry, this is wrong. Butane. I should write butane. Let me correct that. This is not butane. This is butane. Right? Okay. So this is a butane. So butane, you know, it is also 4 carbon compound. It is a but means 4. But means 4. N means what? Alkane. No double bond, single bond. So that is why I wrote 4 carbon atom, no double bond. Okay. So here you should carefully identify how many carbons are there and hydrogen as well. Okay. That's a very easy. We will count later on. So butane. Otherwise, our skeleton is same. Our skeleton is same. Butane plus oxygen, we are doing oxidation in presence of V2O5. So this is also same. So product, we are interested in malic anhydride. So product is same, malic anhydride. We have to keep this formula in your memory. Now only thing is we have to guess the byproduct. Okay, by looking at the carbon atom and hydrogen atom in reactant. Okay. So if you look at this butane, you will definitely guess 4 carbons are there. One over here, second, third, and fourth. These 4 carbon atoms are there. So let us look at the product. product is malic anhydride. So here 1, 2, 3, 4 means all 4 carbon atoms which are present in the reactor, they all are utilized. They are not wasted. All are there in malic anhydride with desired product. So no carbon dioxide will be produced. That is sure. Okay. Now let us look at the hydrogen atoms. First count hydrogen atoms. So here we have one carbon and it is attached to only single bond, means only one valency is satisfied. Okay, or three are not satisfied. कार्बनची व्हॅलेन्सी किती असते? 4 असते. चारामध्ये एकच सॅटिस्फाय झाली आहे. ओके, म्हणजे जे डेफिनेटली इथे 3 हायड्रोजन आयटम्स आहेत हिडन, 3 हायड्रोजन. ओके, we have same case over here. This carbon also attached with single bond. So definitely 3 valencies must be occupied by hydrogen atoms. So here we have another CH3 group. Means we have 3 plus 3, 6 hydrogen atoms over here. Okay. Now come to this carbon. Now this carbon is attached to 2 sigma bond, one over here and another here, right? It means only 2 valencies are occupied, so 2 are remaining. Means we must have 2 hydrogen atoms attached to this carbon. So here we have CH2 group, right? So 2 hydrogen over here. Now look at this carbon atom, it is also same carbon. Okay. Here this carbon attached to 2 sigma bond, one over here and another over here, means 2 valencies occupied, 2 are remaining. Means here we have 2 hydrogen atoms attached. Okay, CH2. We have CH2 group over here. Means in both the positions we have 2 CH2 group. So let us count hydrogen now. 3 over here, 3 plus 3, 6. Here 2 hydrogen, 6 plus 2, 8 plus here 2 hydrogen. Means total 10. Okay, so we have C4H10. Okay, that is what a butane. Now 10 hydrogen atoms we have provided from reactant side. Let us see whether they are accommodated in product or not. So in product, malic anhydride, here we have no hydrogen, no hydrogen, no hydrogen, no hydrogen, no hydrogen, no hydrogen over here. Only here we have one hydrogen because 3 sigma bond attached to carbon means 4 valencies hydrogen. Here also 3 sigma bond, 4 valencies hydrogen. Means only 2 hydrogen atoms are accommodated in desired product. Okay, out of 10 इथे आपले 10 होते, फक्त 2च हायड्रोजन ॲटम आपल्या डिझायर्ड प्रॉडक्ट मध्ये राहिले. दॅट मीन्स 10 minus 2 means 8 hydrogen atoms are wasted. Okay, so those hydrogen atoms will be producing what? Water molecules. How many water molecules? We have 8 hydrogen atoms remaining. So 8 means 4 into 2, 8. That is why I wrote 4H2. Okay, 8 hydrogen atoms will definitely give 4 water molecules. That is what simple logic. Okay, so we are able to write the skeleton, main skeleton of a reaction. Now we just have to balance out number of oxygen atoms. We just count oxygen atoms present in the reactor. Sorry, in the major product. Major product is malic anhydride. Here we have one oxygen, second oxygen, third oxygen. This 3 oxygen over here, and this 4 oxygens. 3 plus 4, 7. So I have 7 oxygen atoms at the production. So I must provide 7 oxygen atoms from or at the reactant side. 7 oxygen atoms means 7 by 2 oxygen molecule. Okay, 7 by 2 is 3.5. So therefore I wrote 3.5 oxygen molecule should be supplied. Okay, so butane plus 3.5 oxygen molecules. After treating with V2O5, we get malic anhydride. Okay, we get malic anhydride and 4H2 molecules are removed as a byproduct. Okay, so this is now balanced reaction for malic anhydride synthesis from butane. Now let us calculate atom economy. So for atom economy, we need molecular formula. So formula C4H, actually it must be 10, right? This is wrong. This is mistake. Actually, I have corrected that, but here it is not reflecting. So I am correcting over here only. So this is 10, right? Okay, okay. C4H10. We got 3 over here, 3 plus 3, 6, plus 2, 8, plus 2, 10. C4H10. Actually, alkanes are actually CnH2n plus 2. CnH2n plus 2. So if n is a 4, okay, so H2n plus 2 means what? 10. Definitely it is 10. So this is butane, this is oxygen, V2O5, we get C4H2O3. This we have already calculated, 4H2. So atomic economy will be 98 is a total molecular weight of a product. Means total molecular weight of malate and hydride, 98. Upon molecular weight of all reactants, means these two and not V2O5, right? So this two is what? Butane. So butane is 58. Okay, 58 plus 3.5 into 32. Why 32? Because one molecule of oxygen is 32, 6 into 30. And if you think 3.5 molecules आपल्याला लागेल. So 3.5 into 32. So that is what total number of oxygen. So into 100. So total molecular weight of a desired product means malic anhydride upon reactant. Reactant is butane, right? Butane plus 3.5 into 32. So it becomes 57.60. So atom economy is 57.64. It is lesser than that for butene. लास्ट रिएक्शन आपण ब्युटीची बघितली त्याच्यामध्ये आपली आयटम इकॉनॉमी जास्त होती. ओके 65% होती. Here it is reduced because number of water molecules are more. Okay, but this is larger. This is larger than that for from the benzene. This from the first reaction, benzene. We got just 44%. Okay, so with benzene we got 44% atom economy. With butene we got with butene, we got 65%, so it is enhanced in the second reaction. But in third reaction, butane, it is reduced, little bit reduced, 57.64%, right? So if we look at the overall reaction, overall I mean scenario, we should prefer second synthetic route. Means prepare malic anhydride from we should prepare malic anhydride from butene to butene because atom economy is 65% in the second reaction, and we will not prefer first route from benzene where atom economy is 44%. We are wasting few atoms. And also here atom economy is a 57.64 means 58% atom economy, and lesser than that for butane. So we should butane. So we should prefer butene route, which is that I will show you again. So so this is what the desirable route. Okay, this is best route for us. Here we got 64.47%. So the answer of the question will be we should prefer uh, 2-butene for the manufacturing of malic anhydride because atom economy is highest in this case. That's what your answer. Okay, so for all such products, we should find out atom economy and we should prefer those synthetic routes or those reactions where atom economy is maximum. Okay, so atom economy maximum means there is a less waste. Okay, now we will have few more reactions to calculate atom economy. Simple reaction we will take. I will write reaction. Sorry. Okay. Uh, Suppose, uh, so I will take fresh slide. Okay, this is better for us. Uh, First example would be benzene, right? Uh, I will write name of the compound. Benzene plus chlorine, chlorine, chlorine gas, obviously. So what we have is chlorobenzene product. I will write over here chlorobenzene, okay, plus I guess the product, the byproduct is produced, and that is HCl, is hydrochloric acid. So this is what the reaction given to you. And if I ask you to calculate atom economy of the reaction, okay. So what you should do? You should write the reaction in terms of chemical formula or molecular structure. So benzene you know well. Benzene is this compound, C6H6. Okay, one bond over here, second and third. This is our benzene. Then chlorine. Chlorine means chlorine gas, you know well. It is Cl2. Okay. So what I will get after performing the reaction? There is a substitution. One of the hydrogen atom, okay, at any one of these six positions. All six positions are equivalent. Okay, six carbons are there. One, two, three, four, five, and six. All six are equivalent. So, at every position there is one hydrogen. So that hydrogen will be replaced by chlorine, and we will get substitution reaction. You see, there is a replacement of one of the hydrogen by chlorine. So this is basically chlorobenzene. Chlorobenzene. Plus, now is that hydrogen replaced by chlorine, that will react with remaining chlorine atom, and here we will get HCl. So this is what a very simple organic synthetic reaction we use in industry for manufacturing of several products. Okay, so our interest is to find out the atom economy of this reaction, because there is a byproduct. So definitely atom economy is not 100%. Okay, so let us calculate that. So how to calculate that atom economy? We should know the molecular formula cost. So here molecular formula, how to write? Just count carbon. 1, 2, 3, 4, 5, 6. 6 carbon. C6. Hydrogen. Here 3 bond means 1 hydrogen. 1. Here also 1, 2, 3, 4, 5, 6. So H6. C6, H6 is benzene, you know well. This is benzene. Okay. So C6H6 plus Cl2. So that we ready-made molecular formula we have. So there are two Cl. Okay. So what we have is this. Here, here now you should carefully write the molecular formula. Just count carbon. 1, 2, 3, 4, 5, 6. So carbon atoms intact, no wastage of carbon. C6, all are there in desired product. What about hydrogen? Hydrogen, here we have one hydrogen because three bonds, 1, 2, and 3. This is one hydrogen. Here also three bonds, 1, 2, and 3. So second hydrogen, third, fourth, fifth. But what about this position? Here there is no hydrogen. Hydrogen is missing. It is lost as HCl, right? So only C6H5. C6H5. 1, 2, 3, 4, 5. Only 5 hydrogen atoms are retained. One hydrogen atom lost as a HCl. Okay, but we have Cl molecule added at this position, right? So that we should consider in a molecular form. So C6H5Cl. This is very important. And remaining is a byproduct HCl that we don't consider. Okay. So percentage atom economy is equal to what? Molecular weight of molecular weight of product, desired product. This is molecular weight of this. So I should write the molecular weight of C6H5Cl, right? Product and not byproduct, divided by what I should write? Total molecular weight of all reactant. Means first reactant is benzene. So I should write molecular weight of benzene C6H6 plus. So I will write this in a bracket, right? Molecular weight of benzene plus chlorine. Okay, another reactant is chlorine here into 100 into 100. You see, so molecular weight of product is chlorobenzene, okay, divided by molecular weight of reactant. Reactant is benzene and chlorine. You can easily identify at LHS. We have two reactants. So we want molecular weight of C6H5Cl. So how to calculate that? So you come at the molecular formula. C6 means one carbon is 12. One carbon is 12, right? So 12 into 6 means 72 plus 5, 1 into 5 plus 1 chlorine, 35.5. Altogether it is how much? It becomes 112.5. So that is equal to 112.1 molecular weight of product, right? Divided by molecular weight of reactant, benzene. First benzene. So benzene means how much? 12 into 6 means 72 plus 1 into 6 means 6 means 72 plus 6 means 78. Right? 78 plus plus chlorine. So chlorine molecular weight. So one chlorine means how much? 35.5. One atom is 35.5. It's atomic weight. Okay. So we have two chlorine atoms in a molecule. So 2 into 35.5 means 35, 35, 70, 0.5, 0.5 is 1, so it becomes 71 into 100. We have to calculate this. So it comes to the 75.5%. 75.5%. So comparatively good atom economy we can say, right? 75.5%. So this is the way you should use, okay, for calculation of atom economy. So for that purpose, you should be able to write a balanced chemical reaction with correct structure. So once this is done, this step is done, the remaining part is very easy. You have to first extract out number of carbon and hydrogen, okay, whatever there in a molecule. Means you basically you should be able to write correct molecular formula, okay. Then for all reactant, reagent and product. So for that molecular formula should be correct. You should not miss single atom, okay, because this is atom economy. And once you did this, okay, remaining task is very simple. You just have to add atoms or atomic weights of the atoms present in the molecule, that is molecular weight, and substitute in the formula. You will get atom economy like this. Okay, so based on atom economy only we decide whether the given route is feasible or not, useful in industry or not. That we decide. Okay, that we decide according to atom economy only. So this is very important part or important principle with respect to green chemistry. Okay, so so here we will wind up for today. Okay, we will stop here. So next time we will meet with a few more reactions